The new section is entitled Lagrange Multipliers. It's a different way of maximizing and minimizing functions given some constraints. Assume for all these problems that the variables are positive. Assume that all the variables are positive. And suppose you wanted to maximize f of xy equals xy, subject to the constraint that x plus y equals 10. Now, how I see this problem is if I double the constraint, I get this, and I want to maximize xy. Well, what I think of is a rectangle. I have some rectangle xy, and the perimeter is 2x plus 2y, which is, 20. I double both sides. Well, I know that. If the perimeter is 20, I divide by 4, and all sides should be 5. And for the record, x plus y really does equal 10. So I know the answer. The answer is x and y should be equal to 5, and the max volume will be, or area, will be 5 times 5, or 25. So this is really just a Calc 1 problem. Okay, I mean, we have that the area is xy, and I have that x plus y is 10, so y is 10 minus x. So it's x times the new way of writing y, which is 10x minus 2x. I take the derivative, I get 10 minus x squared. I take the derivative, I get 10 minus 2x. This is equal to 0 when x is 5. And if x plus y is, 10 minus 5 is 5, so y is 5. And the max area is x times y, which is 25. And for students, did it that way, unless I said to use Lagrange multipliers, this is fine. But this problem says to use Lagrange multipliers. The first thing you want to do is you want to solve that, get the right side or one side to be 0. I subtract 10 from both sides. And we define that function to be g of xy. G of xy is x plus y minus 10. Now, I want to find the gradient of g of xy. With respect to x, the partial is 1. It only comes from here. With respect to y, the partial is also 1. But I don't just want the gradient of g. I want lambda times the gradient of g. And again, I just use different notation, or possibly I'm using different notation. Whenever in these strange looking brackets I put AB, well, I mean AI plus BJ. If there's a third component ever, it'll be plus CK. It's just notation. And I distribute the lambda, and I get lambda lambda. Lambda times 1, comma, lambda times 1. Lambda lambda. Okay. And now I find the gradient of f of xy. With respect to x, the derivative is y. With respect to y, the partial is x. Now I set these two equal. I set these two equal. That is, I set these two equal to one another. Lambda lambda is equal to yx. So the first components must be equal. Lambda must be y. Lambda must be x. Well, if y and x both equal the same thing, then they must equal one another. We may not know what lambda is, but we know whatever it is, x and y equals lambda. That is, they equal one another. So this implies that x is equal to y. Now, I use my constraint. I know that x plus y is 10. Now, you can just think. These are both the same numbers, and they add up to 10. Boom! They both equal 5. But if you can't do that, another way of writing y is x. That x plus x is 10. 2x is 10. 2 times 5 is 10, so x is 5. But x equals y, so y is 5. And the max of f of x, y is f of 5, 5, which is the x value times the y value, that is 5 times 5, or 25. The 25 is the max value of f, and it happens at 5, 5. It happens when x is 5 and y is 5. But we already knew that using Calc 1. Sometimes you can go back and use the other techniques. Here, we want to minimize f of xy, which is x squared plus y squared, subject to the constraint x plus y equals 4. Well, we've done this problem, possibly the same exact one, but definitely a similar one, in the previous section. Applications of extreme is functions of two variables. We told you x plus y is 4, and we wanted to minimize the sum of the squares. It's going to happen when x and y are equal again. But we can do this. We need to find g of x. We take the constraint and we set it equal to 0. That is, we take away 4 from both sides. We get it to equal 0. Okay, and then the gradient of g of xy is, well, here are the three terms. With respect to x, the partial is 1. Partial of that is 0. That's 0. 1 plus 0 minus 0 is 1. With respect to y, you get 0 plus 1 minus 0, which again is 1. But this one, you multiply by lambda. And you get lambda. Lambda times 1, lambda times 1. Now we want to find the partial of f of xy. Well, with respect to x, this partial is 2x, and that's 0. With respect to y, this is 0, plus that partial is 2y. So we set these equal to one another. We set lambda times the gradient of the constraint equal to the gradient of the original function. So lambda is 2x and lambda is 2y. Well, I don't care what these are. If they both equal lambda, then you write them down and you put two horizontal lines between them because they're equal. If two things equal lambda, then they equal one another. But this implies that x is equal to y. Divide both sides by 2. If you multiply two numbers by 2, and you got equality, if two students put numbers in their calculators and they multiply them both by 2, and they got the same answer, they started off with the same numbers. Okay, now we know that x plus y is nothing but 4. But x is y. That is, instead of x, I can write y. So 2y is 4. 2 times some number is 4. That number is 2. And y equals x. That is, x and y are equal. the min of f of xy is f of 2, 2, which is x squared plus y squared, which is 4 plus 4, which is good old 8. That's the least you can get. If two numbers add up to 4, if two positive numbers add up to 4, well, if you squared those two numbers and added them up, you'll never get below 8. We do not have to. Okay, the next one. They want us to maximize, and here we have a function of 3 variables. So this one seems like it's going to be different than the first 1 or 2 that we've done in this chapter or section. Here we're going to have 2 constraints. We're subject to the sum of these 3 variables is 32, and x minus y plus z is 0. Okay. So what you want to do is figure out what g of xy is. Take the first constraint, get it equal to 0. It is take away 32 from both sides. The second constraint, we'll set it equal to 0, and we'll call that h of xy. It already equals 0. So it's just x minus y plus z. X minus y plus z. And now we find the gradient of all 3 functions, these 2 and the one on the top. The gradient of g is, well, with respect to x, that of these, for these 4 terms, only this term has an x in it. Its partial is 1. Only this term has a y in it. Its partial is 1. Only this term has a z in it. Its partial is 1. This one gets multiplied, say, by lambda. And when you distribute the lambda, you get lambda, lambda, lambda. Okay, now we find the gradient of h. There are 3 terms. Only the first one is a function of x. Its partial is 1. Only the second one is a function of y. Its partial is negative 1. Positive z. Its partial is 1. We're going to multiply this by mu. You want to use a and b instead of lambda and mu? Doesn't matter. You get mu times 1, which is mu. Mu times negative 1 is negative mu. Mu times 1 is mu. We want to add these up. So lambda gradient g plus mu times the gradient of h. This is lambda plus mu, lambda plus mu, lambda minus mu, and lambda plus mu. And this is supposed to equal to the gradient of f. The gradient of f of xy is, well, x, y, z. A constant times x. The partial is just a constant with respect to y. Think of x, y, z as x, z times y. You have a constant times y. The partial is x, z. Think of x, y times z. The partial with respect to z is x, y. And then you set the first components equal, the second equal, and the third component equal to one another. And then you solve. We have that lambda plus mu is yz, and we have lambda minus mu is xz, and we have lambda plus mu is xy. Since yz and xy, they equal the same thing, that tells me that xy equals yz. And I've been saying every so often that we are told that in all of these Lagrange multiplier problems, the variables are positive. That is, y is not 0. I can divide both sides by y. So now we just learned that x and z, they're equal. Okay, x and z, they're equal to one another. So I'll go to the first constraint. X plus y plus z is 32. That's z. That's x. X plus x is 2x. So 2x plus y, 32. If I go to the second constraint, which says x minus y plus z is 0, this is x. X plus x is 2x minus y is 0. So 2x minus y is 0. If I were to add these, the y's cancel out, and I get 4x is 32. That means x is 8. But x is the same as z. So now I know x and z. But I know the sum of the three is 32. If x is 8 and z is 8, 8 plus 8 is 16. Each of these are 8. 8 plus 8, 16. If I want to get 32, then y better be 16. Y must be 16. So 8, 16, 8. X, Y, Z. 8, 16, 8. That's the point that maximizes f. If you wanted to know that max value, you just find f of 8, 16, 8. You find f of 8, 16, 8, which is x times y times z, and 64 times 16, that's 1024. And there's the answer. That's the point that gives you the max for f, and that is the max for f. So if they just asked you to find the point, it would stop at 8, 16, 8. If they ask you to find the max value for f of x, y, z, you'd actually have to figure out 8, 16, 8, and then find f of that. Okay. Suppose you wanted now to maximize f of x, y, z, which is x, y plus y, z. Subject to the constraint x plus 2y is 6, and x minus 3z is 0. Now this is an interesting problem, because I could eliminate, say, x. X minus 3z is 0. That implies that x is 3z. Okay, so I can instead solve this problem. I want to maximize f of yz equal 3z, that's x, times y, 3zy plus yz, subject to the constraint that x plus 2y is 6. This can be an alternative problem that you solve. You can solve that with one exception, x, there should be no x's. X is 3z. So there it is. Function of two variables, and you're given one less constraint. Two variables, one constraint. But we won't do it this way. You could, but we won't. Now doing it the way I'm erasing is easier because it will just have one gradient function that you have to find. You have to, from the constraint. Here we have two constraints. We're going to have to come up with two gradients from the constraints. For example, I'll let g of x, y, z be equal to x plus 2y minus 6. And I'll let the second constraint be my h constraint. And it already equals 0. Okay. The gradient of g, well, here are the three terms. The last term, don't worry about it, it's a constant. The gradient of, the partial of x plus 2y with respect to x is 1. With respect to y is 2. With respect to z is 0. You need to be mathematically mature enough to see plus 0z. You need to be mathematically mature enough to see plus 0y. Delta 8, so we want to multiply this one by lambda. Lambda times 1, lambda times 2, lambda times 0. Those three answers are lambda, lambda, 2 lambda, lambda, 2 lambda, and 0. The gradient of h is, well, there's only one term that has an x in it. Its partial is 0. There's only one term that has a y in it. Its partial is 0. There's only one term that has a z in it. Its partial is negative 3. And we multiply by mu. And we get mu times 1, mu times 0, mu times negative 3. Now we want to add up these gradients that came from the constraints. You want to add them up. You add them up component-wise. First components, add the I, you have lambda I plus mu I, 2 lambda j plus 0j. You add component-wise. Okay, and now we find the gradient of f. And these two will be equal. We'll set them equal to the gradient of f. Now f is xy plus yz. With respect to x, this is the only function that has x's in it. The derivative with respect to x is y. Now, both of these functions have y in it. So we're going to be adding. The partial of this with respect to y is x, and this is z. Partial, only this has z in it. The partial with respect to z is y. We want to set these last two equal. That is, lambda plus mu is x, 2 lambda is x plus z, and negative 3 mu, is y. Okay, let's write this up in the corner up here. Then we solve for x, y, and z. We have that lambda plus mu is y. We have 2 lambda is x plus z. And we have negative 3 mu is y. And we have our two constraints. Okay, that's important. We have our two constraints. I make one thing clear. When you go to solve this, when you set the gradients equal to one another, you are allowed to use the constraints as well. It's not just these three equations. It's these two as well. So let's number these. 1, 2, and 3. The third one tells me that mu is negative y over 3. I divided both sides by negative 3. Mu is negative 3. So the second equation tells me that x plus z, actually let's go back to the first equation. No, we're going to go to the first. Lambda plus mu is equal to y. But mu is negative y over 3. If you add them over, you get lambda is 1y plus y over 3, which is plus a third y. Well, that's 4/3 y. And now we know that lambda is 4/3 y. So, going to equation number 2, we know that 2 times lambda is equal to x plus z. Equal to x plus z. That is 8/3 y is x plus z. Multiplying both sides by 3, we get 3x plus 3z. But that tells me that bringing the 8y over, that 3x minus 8y plus 3z is 0. But we know from this constraint that x is 3z. So 3 times 3z is 9z. Plus 3 more z is 12z. We know that 12z minus 8y is 0. Dividing by 4 to make the numbers more friendly, we get this. Which is good, because it's one equation in 2 variables. Now, this first constraint up here, remember x is 3z. So 3z plus 2y is 6. And that's where it all comes together. This is where it all comes together. I got 2 equations and 2 unknowns. If I were to add these, which I kind of ran out of room, oops, erase what I erased. I erased it electronically only. Okay, if you add these 2 equations, see if I can sneak it in. You get 6z equals 6. You get 6z is equal to 6. So z, of course, is 1. And you know that 3z minus 2y is 0. But z is 1. So 3 minus 2y is 0. That means that's 3. 3 minus 3 is 0. So 2y is 3. So y is 3 over 2. So now we have that. Okay. And I guess the next one is simple. We know that x is 3 times z. So x is 3 times 1. 3z. So x is 3 times 1. X is 3. And here's our answer. X is 3. Y is 3/2. And z is 1. That's the point that maximizes f of x, y, z. That's the point that maximizes f of x, y, z. If they ask for the point that maximizes f of x, y, z, you are done. If they want the max, well, f of x, y, z, well, it's x times y plus y times z. And you can factor out this 3 halves. You can factor out the 3 halves. You're left with 3 plus 1, which of course is 4. 3 plus 1 is 4. So the answer will be whatever 3 halves times 4 is. And since 2 goes into 4 3 times, the answer is 3 times 2, or the number 6. So that problem is done. Let us try one more. So they give you 2 constraints. You might be able to eliminate one constraint and one whole variable, or you have to come up with 2 constraint equations, g of xy and say h of xy. Suppose, here's a word problem. Suppose that a cargo container in the shape of a rectangular solid, that is a box, must have a volume of 480 cubic feet. So the volume, which will be x times y times z, length times width times height, and it is 480. And they tell you that they want you to use Lagrange multipliers to find the dimensions of the container of this size that has a minimum cost. So you want to minimize the cost. And they go on to tell you what the cost of some of the sides are. The bottom it costs, it's a good number, $5 a square foot, and the other size is going to cost $3 per square foot. Now, if we call the bottom, we call that the bottom, xy. So the bottom is going to be, well, this area is xy, and we multiply it by 3. Okay. Now, it's going to look differently now, because I don't know how to draw this and make it the bottom anymore. So there is your box. And the bottom is x times y. So the height, that's z. So the bottom is xy, and now all of the bottom costs $5. Excuse me. And we have 5 other sides. The top area is x5, but it only costs $3. So we did the top and the bottom. Now we need to do the left and right side, and the front and the back. Let's do the front and the back first. It's x, well, here is, do it in red. Here is the front. It is x times z plus x times z. But we have 2 of them, the front and the back. And it costs $3 per square foot. Now we have to do the sides. And the sides are going to cost $3, and we have 2 of them. What is this side? Well, it's this, or this, which is y, times the height, which is z. So it's y, z. So c is the function of x, y, and z. Okay, let's get rid of the picture and let's clean up this cost function. For example, 5xy plus 3xy, that's 8xy, plus 6yz, I meant to say xz, of course, 6yz plus 6yz. That is your cost. And you want to minimize. You want to minimize the cost subject to that constraint on top. So you get rid of one of the variables. Now, why don't we just do this in 3 dimensions? Let's just leave it the way it is. So what you want to do is deal with your constraint. Just bring the 480 over. So it's x, y, z minus 480. So delta g will be, now we've done this one already. With respect to x, it's y, z. That is no x, no y, no z. And we multiply it by lambda. Now, the gradient of f is, excuse me, there is no f in this problem, it's called c. The gradient of c is, well, with respect to x, that's 8y, plus, with respect to x, that's 6z. And there are no x's here. Now, with respect to y, the first one is xy, I meant to say x, 8x. The second one has no y's in it. The third term is going to be plus 6z, plus 6z. And with respect to z, you get 6x plus 6y. 6x plus 6y. You want to set these equal. You want to say that this 8y plus 6z is equal to lambda times yz, and you want to say that this 8x plus 6z is equal to lambda xz, and you want to say that this 6x plus 6y is equal to lambda times xy. And we have that. And we basically want to solve that system of equations. We want to solve this system of equations. Okay. Now, if we divide these last two, first thing on the left side, I'm going to factor out a 2. So we get 2 times 4x plus 3z is equal to y x lambda xz. And in this bottom one, I'm going to cross factor out a 6. X plus y, this is equal to lambda xy. And then I divide the two equations. And I get 4x plus 3z divided by x plus y. The lambdas cancel, the x's cancel. X, y, and z are positive. This is equal to z over y. Now, if I were to cross multiply, I get 4xy plus 3yz is equal to xz plus yz. And of course there is one typo, because this should be a 3 down here. This should be a 3. So I get 3xz plus 3yz plus 3yz. And coincidentally, this 3yz is on both sides. So this tells me that 4xy is equal to 3xz. this equals that. I could kill off an x. I can divide both sides by x, and I get 4y is 3z. With dividing by 3, that tells me z is 4/3 y. So if I only knew z or y, I could know the other. If I knew y was 1, then z is 4/3 times 1. If y equals pi over 7, z would be 4/3 times pi over 7. Okay, so what can we do from here? So, using what I'm calling equation number 1, I know that 8y plus 6z is equal to lambda times y times z. The z is 4/3 y. So 8y plus 6z is equal to 4/3 times lambda, 4/3 times lambda times y, which is y squared. And I know that z is 4/3 y. Z is 4/3 y. This becomes 8y. 3 goes into 6 2 times. 2 times 4 is 8. So 8y plus 8y is 16y. This is 4/3 lambda y squared. Dividing by, say, y, the common value, dividing by y, I don't want to lose this statement, that z is 4/3 y. Now dividing by y, we get 16 is 4/3 lambda y. Multiplying both sides by 3/4 to kill this off. If I multiply by 3/4, that's 4. 3 times 4 is 12. We now know that lambda y is 12. Okay, and I obviously need some more space. We now know that lambda y is 12. Now, using equation 3, equation number 3, we know that 6x plus 6y is x times lambda y, or lambda y times x. That is 6 times x plus y this is 12. This is 12x. Actually, let me not distribute. Six x plus something is equal to 12x. What's in that box must be 6x. But it's 6y. That is 6y and 6x are equal. Take away 6x from both sides and you will see that. 6y is 6x. That means x is y. Okay, let me put that down here. These are important statements. X and y, they're the same. X equals y. And lambda y is 12. So let's see if this helps us finally, let's see if this finally helps us figure out x, y, and z. Just messy algebra. Okay. Like I said many times, you are absolutely allowed to use your constraint. Now you know that 480 is equal to x, which is, I'm going to say it's y. Remember, x equals y. It's x times y times z. So z is 4/3 y. That is, you get 4/3 y cubed. This is 480. I'm going to multiply both sides by 3/4. The 4's cancel, the 3's cancels. The right side is y cubed. The left side, 4 goes into 480 120 times. Times it by 3 is 360. So now we are ready to say that y is the cube root 360. But 360 is, what is 360? $360 is 8 times 49. I know the cube root of 8. I have no idea what the cube root of 45 is. So this is y. This is y. X is equal to y. So there is x. Z. Z is 4/3 of this. Z is 4/3 times 2 cube root of 45. Well, 4/3 times 2 happens to be 8/3. So Z is 8/3 times the cube root of 45. And I found the point. It wasn't easy, but I found the point. Let's write it down. That point is, x is 2 times the cube root of 45, y is exactly the same, and z is 8/3 times the cube root of 45. And if you wanted to know the cost, and I'm not going to do this, you'd multiply x and y together and multiply, you'd multiply x and y together and multiply that by 8. Multiply x and z together, multiply that by 6. And then multiply y and z together. In fact, since x and y are the same, this kind of becomes 8x squared plus 12xz. Y is x. X times x is x squared. So that would be a simplified, that would be simpler to compute. You'd only have to square x and multiply x and z. You wouldn't have to multiply x and y and x and z and y and z. That would be 3 multiplications. And then you'd have to do 3 multiplications, and then you'd have to multiply by 6, that's another one, and multiply by 6, that's another one, multiply by 8, that's another one, and then do 2 additions. If you add it first, you would have to do 2 multiplications, and in the third one, x times x is 1. Oh, times 8, that's only the second one. And then you'd have to do x times z, that's 1 multiplication, and multiply that by 12. That's 2 more multiplications. And then you'd have to do 1 addition. Instead of 2 additions, you do 1. Instead of 6 multiplications, you only do 4. But to be honest, you did do 1 extra addition to simplify. It's 2 less multiplications. It's a little bit quicker. And less messy. But then again, 2 of those multiplications are exactly the same. That note that finishes this section. Good luck with that.